Hello everyone. On this video we will be looking at moments of inertia. Okay, so quick review. The moments with respect to the y-axis and respect to the x-axis, which we use to determine not enough room. The center of mass of a lamina are sometimes called the first moments about the x and y axes. Clean that R up a little. Are sometimes called the first moment about the x and y axes. Okay, so what do we know about the moments? Well, we know that a moment is equal to the mass times distance. Okay, so the moment with respect to the x-axis is equal to the double integral of y times rho of xy, yeah. Okay, where of course this is our distance to the x-axis. And of course our rho is our mass. Okay, and we know that the moment with respect to the y-axis is also the double integral over the region times x times a rho of xy respect to the area. Okay, so of course our x is the distance from the y-axis, or distance to y-axis. Yes, depends on how you want to say it. And of course this is your mass. Okay. Now these are called your first moment. Now your second moment is what they call the moment of inertia. The second moment is the moment of inertia. Okay. Of a lamina about a line. Okay, so the moment of inertia, that measures the, I guess you could say, the tendency of matter to resist the change in rotational motion. Okay, so where mass can be used to measure the tendency of matter to resist change in a straight line, okay. Now, in comparison, the actual moment of inertia is a measure of the tendency of matter to resist change in a rotational motion. Okay. So we know that our inertia is equal to mass times the distance squared. Or mass times distance squared. All right. So since we are running out of room, if you are still writing, feel free to press pause. But we're going to go ahead and move on to, well, continue this on our next page. Okay, because first you have to actually show the formulas for our moments in inertia. All right. So the second moments of inertia about the x and y axes will consist of the following formulas. Okay, so I with respect to the x-axis is equal to the double integral over the region y squared times rho of x y with respect to the area. Okay. So of course our y squared is the square of the distance to the x-axis. And of course this once again is our mass. Okay, so the moment of inertia with respect to the y-axis is equal to the double integral over the region of x squared times rho Okay, so of course our x squared is just the squared distance to the y-axis. And of course our rho is our mass. Okay, so that's where our I sub 0 is just equal to the sum of our two second moments of inertia. Okay, so that I sub 0, that's called either the polar moment of inertia or the moment of inertia about the origin. Okay, so if you see either the polar moment or moment of inertia about the origin, that's what they're asking for. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our example. All right, so let's say, for example, just a heads up, this example will take a couple of pages, so you may want to start on a fresh sheet. We want to find the mass. This is problem A. Find the mass and center mass of the lamina that occupies the region D, bounded by y equals 1 minus x squared and y equals 0, with the density function rho of x y equals k times y. Okay, so for problem B, of course, you want to find the moments of inertia. I'll capitalize that I for some reason. IY and I sub 0. Alright, so we're going to go ahead and get started with part A. Okay, so we know that we have our boundaries for y equals 0 and y equals 1 minus x squared. Okay, so we have our y boundaries, we just need our x boundaries. Okay, so we see that y is equal to 1 minus x squared and y equals 0. So that means 1 minus x squared is equal to 0. Or x is equal to positive or negative 1. Okay, so now we have our boundaries for our x. Okay, so the first thing we have to do, we have to find the mass. Okay, because we can't find the center of mass without the first moments and the mass itself. So our mass is equal to the integral from negative 1 to 1 for our x, and our y from 0 to 1 minus x squared of our p of xy dy dx. And of course, we're going to start in the center. So that's going to give us the integral from negative 1 to 1. With respect to y, that's just y squared over 2. So that's ky squared over 2. From 0, remember that's y equals 0 to y equals 1 minus x squared dx. Okay, so of course we plug in our 1 minus x squared. We end up with, we'll just factor out the k over 2, just to make it a little easier. So from negative 1 to 1, so that leaves us with 1 minus x squared squared. So if we have 1 minus x squared squared, once we replace it with y, that just gives us 1 minus 2x squared plus x to the fourth dx. Okay, so 1 minus x squared squared, 1 minus 2x squared plus x to the fourth. Okay, so if we integrate each one of those terms, we end up with, of course, our k over 2. And we integrate that, that's going to give us the integral of x, is just, well, 1 is just x. Okay, so you have x to the third over 3, so you have minus 2/3 x to the third. Integral of x to the fourth is x to the fifth over 5, so that's plus 1/5 x to the fifth, and that's from -1 to 1. Alright, so to simplify that from -1 to 1, we end up with k over 2 times 1 minus 2 over 3 plus 1/5 plus 1 minus 2 over 3 plus 1/5. Okay, so if we go ahead and combine like term and add all these together, we end up with a mass that's equal to 8 over 15k. Okay, so we have our mass. Alright, so now we have to use that mass to find our moment of mass, or our moments of mass. Use those to find our center of mass. Okay, so we have, separate that a little bit. Our first moment with respect to the y-axis, remember that's equal to -1, 1, and from 0 to 1 minus x squared. Remember that's x times your p of x. So that's going to be x times k times y, or you can just make it k xy dy dx. And if we integrate the center, that's from -1 to 1. And just with respect to y, that's kx times y squared over 2. So I'll just make that kx times y squared over 2. And that's from y equals 0 to 1 minus x squared. Okay, so the k, we're going to go ahead and factor out the k in the 1/2. Just like we did up here, just to make it a little easier. So k over 2 times the integral from -1 to 1. That's just going to leave us with x times 1 minus x squared squared. Dx. Okay, so if we multiply this out, foiling this one, and then multiply each term by x, we get k over 2 times the integral from -1 to 1 of x minus 2x to the third plus x to the fifth with respect to x. Alright. So from there, we go ahead and integrate each one of those sections there. We have k over 2 times x squared over 2 minus x to the fourth over 4, which is just x to the fourth over 2, plus x to the 6th over 6 and that's from -1 to 1. All right. So if we plug everything in, we have k over 2 times 1/2 minus 1/2 plus 1/6 minus 1/2 plus 1/2 minus 1/6, which actually will equal 0 once we're done canceling out everything. Okay, so our moment of mass, or our first moment, in the direction of the y-axis is equal to 0. Okay, so we're running out of space. We're going to continue this on the next page. If you are still writing, feel free to press pause, but we're going to go ahead and continue on our next page. All right, so we're going to continue our moment of mass in the x direction. That's going to equal the integral from -1 to 1 times the integral from 0 to 1 minus x squared. Okay, so that would be y times our rho of x. So you have y times k times y, which is k y squared dy dx. Okay, so just like before, we're going to go ahead and start in the middle. So from -1 to 1, with respect to y, that's y to the third over 3. So that's ky to the third over 3. And that's from y equals 0 to y equals 1 minus x squared with respect to x. Alright, so if we go ahead and simplify that, we have from -1 to 1, we have 1 minus x squared. If we go ahead and factor out the k over 3, just to simplify that a little bit, we have y to the third, so we have 1 minus x squared to the third. Okay, and of course we plug in the y equals 0, we just get 0, so we don't bother with that one. Okay, so 1 minus x squared to the third will just equal, from -1 to 1, 1 minus 3x squared plus 3x to the fourth minus x to the sixth power with respect to x. Alright, so if we go ahead and integrate each one of those terms, we end up with k over 3 times x minus, so we have x to the third over 3, the 3's cancel, that's minus x to the third, plus you have x to the fifth power over 5, so that's 3 over 5x to the fifth power, minus x to the seventh power over 7, so that's 1 over 7 times x to the seventh power, and that's from -1 to 1. Alright, so we go ahead and plug those in. That will equal 1 minus 1 plus 3/5 minus 1/7 plus 1 minus 1 plus 3/5 minus 1 over 7. All right. Okay, so if you multiply what's left in here by k over 3, by the time you finish combining like terms, you should get 32k divided by 105. Okay, so your moment of mass with respect to the x-axis is 32k divided by 105. Okay, so now we can go ahead and just find our center of mass. Okay, so that means that our mass, which is 8k over 15, we solved for that earlier, and our x bar, which is our moment of mass with respect to the y-axis divided by our mass, that's equal to 0 over 8 over 15k, which is just 0. Okay, so now our y bar, which is our moment of mass with respect to the x-axis divided by our mass, is equal to 32k divided by 105 divided by 8k over 15. Or you can just write that out as 32k divided by 105 times the reciprocal of that, which is 15 over 8k, which is 4 over 7. Okay, so now we know that our x bar, y bar is equal to the coordinates 0, 4 over 7. Okay, so we have our center of mass. All right, so that's it for problem A. Now we just have to go ahead and finish off problem B. So we're going to start that on a new sheet. So if you are still writing, feel free to press pause. But we're going to go ahead and finish this up on our next sheet. All right, so for problem B, we have to find our moment of inertia with respect to the x, which is equal to the integral of our region times y squared times rho of xy with respect to the area. Okay, so that will be equal to the integral from -1 to 1 and from 0 to 1 minus x squared of y squared times our rho, which is ky, dy dx. Clean up that y a little bit. Okay, so if we go ahead and just combine those two, we have our double integral from -1 to 1 and from 0 to 1 minus x squared of k times y to the third dy dx. Okay, which is equal to the integral from -1 to 1. If we go ahead and integrate right in the middle with respect to y, we get y to the 4th over 4. So that's ky to the 4th over 4, and that's from 0 to 1 minus x squared dx. Okay, so if we go ahead and factor out the k over 4, just to make things a little easier, integral from -1 to 1, that's 1 minus x squared to the 4th power with respect to x. Okay, so if we go ahead and factor all of that out, we have k over 4, the integral from -1 to 1 of x to the 8th power minus 4x to the 6th power plus 6x to the 4th power minus 4x squared plus 1 with respect to x. All right. So if we go ahead and integrate each one of those terms with respect to x, we get k over 4 times x to the 9th over 9 minus 4 over, well, x to the 7th over 7, so that's 4 over 7x to the 7th, plus x to the 5th over 5, so that's 6 over 5x to the 5th, minus x to the 3rd over 3, so that's 4 over 3x to the 3rd, plus x. And that's from -1 to 1. Okay, so kind of bypassing, plugging everything in. Once we plug in the 1 and the negative ones, we just end up with 64k over 315. All right, so now you go ahead and find our moment of inertia in the direction of the y-axis, or with respect to y. Make that a little smaller. Okay, so we can see there that that's going to equal the double integral of x squared times our rho of xy. Okay, which is equal to the integral from -1 to 1 and from 0 to 1 minus x squared of x squared times our kx, well, times our k. So we can just make that ky times x squared or kx squared y, dy dx. Okay, so our rho, remember that's our ky, just times x squared. All right, so if we go ahead and integrate the middle, that's the integral from -1 to 1. Just respect to y, you have kx squared as your constant, so that's y squared over 2. So that's kx squared, y squared over 2. And that's from 0, or y equals 0, to y equals 1 minus x squared. And of course, can't forget our dx. Okay, so if we go ahead and factor out the k and the 2, that's k over 2, and the integral from -1 to 1. We plug in our 1 minus x squared for our y, we end up with x squared times 1 minus x squared. Of course, when we plug in the 0, we get 0. So we have x squared times 1 minus x squared squared with respect to x. We can go ahead and FOIL this one out and distribute the x squared. And that will give us our k over 2 times the integral from -1 to 1, x squared minus 2x to the 4th plus x to the 6th with respect to x. All right, so if we go ahead and integrate these, we will end up with k over 2 times x to the 3rd over 3 minus 2/5 x to the 5th plus x to the 7th over 7. And that's from -1 to 1. Okay. So plugging in all of our values, combining like terms, you will end up with 8k over 105. Okay, so that's our I sub x and our I sub y. Okay, so that means our polar moment of inertia which is equal to the sum of our second moment, is 64 over 315K plus 8 over 105K. All right, so if we go ahead and multiply this by 3 over 3 to get like terms and then add, we end up with 88 over 315K for our polar moment of inertia. Okay, so it was pretty lengthy example problem, but we eventually reached our goal. All right, so hopefully this video, although long for this one problem, hopefully it made sense, and I will see you on the next video.